Hello, it is Robert Guderian, and today we will continue our adventure on numpy, and we're going to find out how we make arrays and what's new about it. So the first thing is that this is a big new library that we'll be using, and we will require an import. And this import looks a little different than we've seen, but it's something that we'll just memorize, and that's okay. Actually, in our case, we just get to copy and paste it. I'm not a huge fan of doing this. Import numpy as np. This just will rename our library import. That's all it's doing. So instead of saying numpy.array, we're going to use np.array. This is what everyone does. This is what every example is on the internet. This is what the textbook does. I'll suck it up. It's okay. In the end, it's all the same. And then we want to make an array. It's actually fairly simple. What we can do is pass it a existing list or any kind of iteratable data type. You come here for the how Rob speaks, right? And boom, my array, and we'll make that bigger too, is now an array. And it actually looks slightly different. If we print it out here, it'll print out in a different way, and that's fine. This is just a text representation of our array, and it probably should look different than a list. So that's it. We did it. One of the pages I made for numpy is that it's going to be more efficient in terms of memory usage. Well, I kind of ruined that, didn't I? I am now storing this data set twice. So I can even reshape this to be that. It'll be the same code. And now I have data, which is an array, and I have, or data, which is a list, and my array, which is a numpy array. And both of them get represented in our variable explorer, which is very nice, but I'm not really saving anything, am I? So this is not the ideal way of making a numpy array. It is useful if you have a data set and just want to convert it. It's here for us, and it's really easy. Easy is good. Okay, what if I do this? We know that Python lists can just happily accept a string, but I mentioned that numpy arrays are one data type. So how will this be resolved? So I'm just going to happily put an A in here, and I'm going to go here and just say print my array because I just want it to print out, and we're going to look at it, and there's quotes around them. Let's see what 1 plus 1 is. These are all strings. So my array at spot 0, we can just index them, plus my array at spot 0, legitimately 1 plus 1 is now 11. So yeah, it uses string appending because what numpy did for us was say, okay, you gave me a list. There's a bunch of data in it, and it has to choose the most permissive data type. Integers are the most restrictive. You can only have whole numbers. Floats, you can have real numbers. Strings, you can represent pretty much anything as long as you can represent it as a string, which includes all numbers. So it converted my whole numpy array into strings. And we can actually check that. dtype. dtype. I believe this works. It's a very funny way of saying Unicode. So that's not great. That is a big accident that we can accidentally do, which will usually not be what we wanted to do. Generally, if we want to check our data type, you can say my array or whatever your numpy array is, .dtype, and this one is an int64. Okay, well, that's good. int64 is what it should be if I'm passing it all integers. So numpy will try to be kind to us. It will not crash. It will just put it to the most permissive type, which is not always what we want. Okay, what if we add a decimal place? So pretty easy to do. Just put even 1.0, which is still technically maybe a integer. It's going to change the whole thing into floating point numbers. And interestingly enough, represent them in scientific notation. generally it just shows a decimal place. Well, let's take this one down a notch. And then it should just give me some nice decimal places. There you go. Usually it'll just say number and then a dot. And that will tell you that we're looking at a floating point number. If we run dtype on this, it's going to be a float 64. Indeed it is. Which is actually pretty much the same floating point we use in normal Python, just for the record. I've already done this for you once, but there should be no surprise here. We can index data. It's exactly the same as from lists, where we can just say, give it an index in square brackets, and we can either get that data out or set new data. So in this case, I will jump over to here and say my array at spot 2, just to change it up. We're going to change 42 to be 9001. Why? Because it's over 9,000. And then, whoop, that's not what I wanted. Cancel. If I just run this, I guess I didn't have to. What am I doing? I lost my train of thought. My array at spot 2 is equal to 9001. And then if I just print out my array, by typing it, it will go back to scientific notation for me. And you'll see that it changed. Pulling out data is the same thing. You saw me do this once already, where I can get the data at spot 0. And the negative notation stuff works too, because reasons. I'm not a huge fan of that, but that's okay. I didn't write Python. Somebody else did, and they did a great job. Okay, so it feels a lot like our list format. That's great, because it's a nice abstraction on what's getting stored. We just have this idea of being able to index things, and that's exactly what we want. We have a whole bunch of functions for making arrays. We've seen np.array, where we pass it in some kind of data that we can iterate over, and then it'll just happily make an array out of it. Arange is the next one that we want to look at, which is like range, just different. Start, stop, step. That's the exact same setup that we had for range. So I could say range, I have to pass it into a list because Python is mean. Range, starting at 4, go up to 10, and step by 2, give me all the evens, and I need to close those brackets, and I need to show you that code, and it'll do that. And np.arange will do the same thing for 10 and 2, and it'll be a numpy array instead. Okay, so that's nothing new to us. We can leave off terms exactly like we did with range. They recreated it completely. Because this one is the quote-unquote easy one. Let's look at the documentation. And I will move that over into here. Start, stop, step. If you see square brackets in the documentation, that does mean that it is optional. And there's a whole mini language. Of course there's a mini language. We're programmers that defines this. There's also this one. We've used some key value stuff in creating, in calling functions before. I've done the end is equal to empty string for print. This has that same thing, and this is what it looks like in documentation. And let's actually mess around with this just a little bit. So I would just want to set my dtype. I can still set it by using the order. So that is like how we create functions and call functions. We just have the order, and then we put our arguments in the order that the function expects it, and magic happens. So I'm going to add dtype into my np array. So I actually want my arange to be floats because I think that's exciting. So all I have to do is say np.float 64. And then it'll make them into floating point numbers. So you can see the decimal place, which is enough proof for us to know that it's a float 64. So that's nice. But let's say that I don't want to give it the start point. I can leave this off. If I just do this, it's going to be grumpy with me. But if I use the key value pair thing, where I say dtype, type is equal to np's float 64, it'll give me an array, which seems to be empty, of float 64s. That's interesting. Oh, okay. Let's just give it one argument. It went from 10 to 2 because of the arguments I gave it, because I left off the step. So there you go. A range, if I just say 10, it'll go from 0 up to a not including 10 and give them in floats. Don't worry too much about that. We probably won't need to set our D type. Usually numpy will do it for us, but if we ever need to force it and tell it, no, 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 I want this to be an integer, or no, 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 I want this to be a float, every time we can say, hey, Python, numpy, do the thing. I want it this way. This all goes to the meme of do what I tell you to do, no, do what I want you to do, not what I tell you to do. This is us telling it exactly what to do in no uncertain terms, which is nice. Linspace is our next one. This one is interesting. So much so that I need to draw what the heck it's doing. So let's do this in on the iPad. And what linspace does is it divides up from the slide between A and B with K pieces. Like, what the heck does that mean? Ooh, ooh. Come on, there we go. So let's the 0 to 1 is the best example for this. So 0 to 1, and it's going to put it up into K pieces. My K in that example is 5. 1, 2, 3, 4, 5. So now I have 5 pieces. So it's going to give me 5 numbers, and it's going to take this space from 0 up to and including, oh no, you know that Rob doesn't like this, the endpoint. And linspace is for a linear space. So the idea is that you're taking some endpoints and dividing that into K pieces, and you're going to probably change K. And when we're doing experiments, this is useful. It'll give us more resolution. And the question is, how much resolution do you want? And it'll draw us a line with more or less dots on it to do that for us. So how would we actually divide up the space? Well, what is half of 0 and 1? That is 0.5. And then this must be 0.75. This must be 0.25. This is 0. This is 1. That's what it's going to give back to me. The same, if we think about from 0 to 10, which is the 1 to 10, and then divide that into 10 pieces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I can move 10 over a bit, can't I? There we go. Win. So then we're going to have, this is going to be 1. This is going to be 10. And then we actually know we have 10 pieces. So this will actually count normally, which is nice. But if I put that down to 0, it's going to slice it up into math I cannot do in my head. And it'll slice up the space between 0 and 10 into 10 pieces, which is not going to be beautiful integer numbers. What does that all mean? Why would we use this? Once we start doing plotting, this is actually quite beautiful. And we'll do a little bit of plotting to show you what we mean. np.linspace from 0 to 1 and bust that into 5 pieces is exactly what I predicted. And if we do 1 to 10, 1 to 10, and then 10 pieces, this will be, that's the 0 to 10 with all the weird numbers I can't do in my head. 1 to 10 will be 10 pieces and will be smooth and integer numbers that make sense in our brains. Put it to 5, it'll put it into 5 pieces, which is, it starts putting it into floating point numbers. But all we have to really know is this. We have a start point, end point, and then including those pieces, we're going to have N or K pieces with the letter I used, chunks between. This will be more beautiful when you start doing some graphing. For now, we just want to know that it exists, and we'll come back to it once we start doing some graphing and some pretty things. Whew. Okay, zeros. This is probably the weirdest one. It's also the most useful. It's also how every other programming language works. Generally, in a proper programming language, when you request an array, it is initialized to zeros. Or in the case of objects, null, which is actually still technically 0 in that case. And this feels weird. And like, I'm not even gonna run the code for you. It's just gonna give me zeros. But the idea is that you set up your array and then you can start filling it. And you want that default value of 0 to be the automatic placeholder. This is really nice for when you actually know how many data points you have. And then you can just fill it in. Or we're going to start making 2D arrays, and we're going to want that to be all zeros, and then we can start filling in all our data. Yeah, this is the standard way of doing it. But again, there's just no data in it for us. So we start filling it. But we'll know that everything else is 0, and we don't have to always fill each spot because we'll know that it's 0. NP.1s, same thing, except it's all 1s. Don't know why that exists. Truth be told, no idea. NP.random. We all love random numbers. Well, everyone knows I do. This will give us a whole bunch of random numbers. Cool. Tell me more. I'll run it over here. This is when the interactive console is really nice, just for hacking around. np.random.rand 100. It'll just give me 100 values in a huge array, and they're pseudo-random. There is a seed, which we can set. I'll do 20 so we can actually see it. And by default, they are from 0 up to and not including 1. And that's nice. And we can also start giving it shapes. Rand int is very nice, which will give us random numbers from a start point to an end point, and then how many you have. Okay, cool. Because I'm a nerd and whatever, we're gonna redo the dice rolls using numpy, and that is how I'm gonna prove to you that this is smoking fast, and it's actually pretty cool. But that is for another day. Today we're just seeing how to create these things. Slicing. Does it work? Of course it does. There is actually more to it in NumPy, but all of the basic slicing stuff that we saw with Python lists will work here too. So I don't even need to demo that for you. You are experts in that. So overall, it does feel the same as the list, and often you can use them interchangeably, but NumPy is faster. And it's certainly not a list, and we're going to start building up on it more and more and more, and fixed size, fixed size, fixed size. So overall, read the documentation, and I'll let the GIF finish. GIF. Have a good day.